Dear students, in this section we are going to deal with the gravitational force and the motion of satellites. We know the gravity or the gravitation is a natural phenomenon by which all things with a mass or energy, including planets, stars, galaxies and even light, are brought towards one another. It is the gravity that binds us to the Earth and hold the Earth and the other planets in the solar system. The gravity gives weight to the physical objects, and the Moon's gravity causes the ocean tide. The gravitational attraction between the original gaseous matter present in the universe caused it to forming stars and caused the stars to group together into galaxies. So, the gravity is responsible for many of the large-scale structures in the universe. In short, it is the gravity that holds the entire universe together. Today, we are going to discuss the law which is behind the gravitation. It is formulated by Sir Isaac Newton, and it is known in his name, that is Newton's law of gravitation. It states that every body in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Suppose, if we have the two masses, m1 and m2, and if they are separated by a distance t, then according to the Newton's law of gravitation, the force of attraction between them is direct. That is, we can represent by F. That is, F is directly proportional to m1, m2, and also it is inversely proportional to the square of the distance between, that is 1 by d square. So we can combine them. F is directly proportional to m1 into m2 divided by d square. Or F is equal to, there is some proportionality constant, that is denoted by capital G into m1 into m2 divided by d square. Now this is the mathematical expression for the Newton's law of gravitation. Here the capital G is called the universal gravitation constant. It is called the universal gravitational constant. And how can we define the universal gravitational constant? So if we have the masses of 1 kilogram each, that means if m1 equal to m2 equal to 1 kilogram, and also if they are separated by a distance 1 meter, that means d is equal to 1 meter, then the expression for the gravitational force becomes F equal to G. That means the gravitational constant is equal to the force of gravity. When or it is the force of gravity exists between the two masses of 1 kilogram each, and if they are separated by a distance 1 meter. So that is the definition of the gravitational constant. That is, G is defined as the numerical value of the force of attraction between two masses of 1 kilogram each separated by a distance 1 meter. From the expression for the gravitational force, we can have the expression for capital G, that is G is equal to F d square by m1 into m2. Okay. So using this equation, we can find the value of the gravitational constant. It was done by Henry Cavendish in 1798, and the value of G is found as 6.67 into 10 raised to negative 11 Newton meter square per kilogram square. Newton meter square per kilogram square. Okay. Because of this value, we can see that the gravitational attraction between small bodies is very negligible. However, if the masses have become very large, as that of the sun and the other planets, the gravitational force become very large in spite of the larger distance between. Okay. Once if we know the value of capital G, we can find the mass of the Earth. So we can calculate the mass of Earth. For that, let us hold a stone on the surface of the Earth. Let small m is the mass of the stone. And the Earth has the mass capital M and the Earth radius capital R. Okay. So the distance from the center of the Earth to the stone is, we can take it as capital R, because we hold the mass, we hold the stone is very close to the surface of the Earth. Okay. Then if small g is the acceleration due to gravity, then what is the gravitational attractive force on the stone? That is nothing but that is the weight. Okay. So small mg is the weight on the stone. That is nothing but that is the gravitational force acting on the stone by the Earth. But we know the expression for the gravitational force from the Newton's law of gravitation. That is capital G m small m divided by r square. That is the gravitational force according to the law of gravitation. Okay. So we can equate these two, because these two expressions gives the same. So G mm divided by r square into small m into G. So we can cancel out the small m, and from that we can have the value of the expression for capital M, the mass of the Earth, is equal to small g r square divided by capital. On the surface of the Earth, the value of small g is equal to 9.8 meter per second square, and the radius of the Earth, that is around that is 6,380 kilometer, and we know the value of capital G, that is 6.67 into 10 raised to negative 11 Newton meter square per kilogram square. Okay, we can substitute this value, that is capital M is equal to 9.8 r square, that is 6,380, when we convert it to meter square divided by the value of capital G, 6.67. So after recalculation, we can have the value of capital M, the mass of the Earth, is 5.98 into 10 raised to 24 kilogram. Okay, so that means we can calculate the mass of the Earth, that is around 5.98 into 10 raised to 24 kilogram. Next we are going to check what is the value of small g. That is at the different positions from the earth. So g, the value of small g on the surface of the earth, that we can have the earth mg is equal to the weight acting on a body of mass m is equal to the gravitational force acting on that body. That is g mm divided by r square. From that, small g is equal to capital Gm divided by r square. Now this is the value of small g on the surface of the earth. Next we are going to see what happened to the value of g when we move up to a given height. Let us see. Suppose if we place a mass of, if we place an object of mass m which is placed at a height h. Okay. Now what is the weight acting on that body? That is equal to m into g. Here the value of g, that is different from the value of g from the on the surface of the earth. Okay. So the weight acting on that body is equal to m into g. That is also equal to, according to the Newton's law of gravitation, we can have the another expression, that is gmm divided by r plus h. So let us write the weight acting on the body when it is at a given height h, that is mgh, because the value of g, here we are using the g as the value of g at a given height. So the weight is equal to mgh. Okay. So that should be equal to, that is same as the expression for the force of gravity between the mass and the earth, that we can express like capital Gm, this small m divided by, instead of r we have to write it, that is r plus h. Okay. So here it is the distance of it is the distance between the mass from the center of the earth. Okay, that is we have to write that distance as r plus h. So r plus h whole square. Okay. Then from that, the gh is equal to gm divided by r plus h whole square. Okay. So let us take the capital R from outside the bracket. Then we can have capital Gm divided by r square 1 plus h by r whole square. Okay. Since r plus h whole square is there, so when we take the r from the bracket, we have to take it out as the square. So that is we take the r square. So in the first time when we take it outside, it becomes 1. So 1 plus, and there is no capital R term in the second time. So we have to write it, that is h by r. Okay. So 1 plus h by r whole square. But what is gm by r square? The gm by r square is nothing but it is the value of g on the surface of the earth. So I can express small g instead of gm by capital R square. Right? The g, that is the value of g on the surface of the earth, that is equal to 1 plus g divided by 1 plus h by r whole square. Okay. Now, again I write G is equal to GH is equal to G into 1 plus H by R raised to -2. So we can make the expansion. So we can use the expansion for the 1 plus x raised to n, that is equal to 1 plus n into x plus n into n minus 1 divided by x factorial into x square and so on. Okay, but here, so we are taking only the first order terms, because compared to the radius, the value of h is less than the value of r. So when we take the ratio h by r, it is less than 1. So when we take the square of that same h by r, it is again very small. So when we take the higher order term, the value becomes very small. So we can neglect the higher order term. We are taking only the first order terms. So GH is equal to G into 1 minus Q H by R. Now this is the expression for the value of G in a given height h from the surface of the earth, and from this you can see that as the height increases, the value of G decreases. Okay, so when we move up, the value of G is less than that value on the surface of the earth. Now we are going to find how the value of G varies with the depth. That is, when we move down to the surface of the earth, what happens to the value? So on the surface of the earth, we know on the surface of the earth we can write T is equal to capital Gm divided by R square. Suppose we have the earth of mass capital M and as the radius capital R, and if rho is the density of the earth, then we can express the capital M in terms of the density and the volume. So capital M is equal to density into volume. So if R is the radius of the earth, the volume of the earth is equal to 4 by 3 pi r cube into density rho. Therefore, we can again express G is equal to, instead of capital M, we can substitute this, that is capital G by R square into M, that is 4 by 3 pi r cube rho. So that is equal to, we can cancel out r square, so 4 by 3 pi G, capital G, rho into capital R. Okay, so we can express the value of G, small g, in terms of the density. Okay, now again look into the figure. If we consider a point capital B at a depth d, okay, So the acceleration due to gravity at the point D is similar to the value of G given by the above equation. So there is a difference, that is, when we consider the value of G in a depth D, we can use this equation, but we have to replace capital R by R minus. We have to replace the capital R by R minus. Okay, so we can have the value of small g at a given depth is given by, that is, we can write, that is, GD is equal to 4 by 3 pi G or R minus D. R minus. Okay, because to the value of small g, only the mass below the point B gives the contribution. Okay, only the mass below the point B gives the contribution towards the gravitation force. Okay, so we can from our initial equation for the 3 pi g rho r, we can find the value of g in a given depth by replacing capital R by R minus. So again, we can take the capital R from the bracket. So R can be taken outside. So that is the equation becomes 4 by 3 G rho R 1 minus D by R. 1 minus D by R. But what is this expression? 4 by 3 pi capital G rho R? That is nothing but that is the value of G, small g, on the surface of the earth. Okay, so we can again GD is equal to G small g into 1 minus D by R. 1 minus D by R. Now this is the expression for the value of G in a given depth D from the surface of the earth. Okay, here also the value of G, the acceleration due to gravity, which again decreases with the depth. Okay. Now we are going to find another parameter. Here the variation of G with the latitude. Variation of G with the latitude. Okay. You already know what are the latitudes and the longitudes. Okay, here the earth is rotating about its axis from east to west with an angular velocity omega. Here what is the angular velocity omega? That is, in the case of earth, the angular velocity is 7.3 into 10 raised to negative 5 radian per second. Okay. So as the body is rotating about its own axis, what happened to an object placed on the surface of the earth? So the body on the surface of the earth experiences an acceleration due to the rotation of the earth. Due to this rotational motion of the earth, the object on the surface of the earth also experiences an acceleration. And this acceleration varies with the latitude. The value of the acceleration is different at a different places on the surface of the earth. Okay. So the effect of this acceleration is to reduce the effective value of acceleration due to gravity. Okay, when the body is already have an acceleration, the effect of that acceleration is reduce the acceleration due to gravity at the given place. Okay, so in the figure you can see there is a particle is situated at a given point, and you see the particle is placed at this point, which is at a latitude theta. So this variation, so there is a variation in the value of g is given by that is g theta is equal to g minus r omega square cos square theta. Here r is the radius of the curve, omega is the angular velocity, and theta is the latitude. Okay, that means there is a variation of g as we move from the equator to the pole. That means it is varies with the latitude. Okay. At the poles you can see theta is equal to 90 degree. Okay, what happened to the value of g theta? G theta is equal to cos 90 is equal to 0. So g theta is equal to g. Okay. And what happened to at the equator? At the equator, what is the value of theta? The latitude is corresponding to the equator is 0 degree. So what happened to the value of g theta? G theta is equal to g minus r omega square. That means the acceleration due to gravity is greater at the pole compared to that at the equator. That we can see that is the value of g is at the pole is greater as compared to the value of g at the equator. And the value of g at the equator is smaller than an amount. Which that amount? That is r omega square. It is smaller than the value of the pole. Okay. So when we calculate this value, you can see that you can take the value of capital R is equal to 6,400 kilometer, and omega that we have already done, that is 7.3 into 10⁻⁵ radian per second. Then we can find that change. Okay, the value of the change in g as compared to the value in poles, the change in the value of g is equal to that is r omega square. That is we can calculate, and that is 0.034 meter per second. That is meter per second square. Okay. So from this value you can make the conclusion that what is that? The variation due to latitude is very, very small. So this is the change. The value of g as we compare it to the poles and equator. The value of g in the equator is less than this amount as compared to the value of g and the poles. So even though there is a change, but this change is very, very small. Okay. And also there is a variation of g due to the size and shape of the earth. We know the shape of the earth is slightly deviates from the perfect sphere. We can see the earth is not a perfect sphere, so it is the radius in the equatorial plane is about 21 kilometer larger than the radius along the poles. Okay, so that means there is a variation in the value of capital R. So due to this equatorial bulge, you can see the equatorial part is little bit bulger than compared to the poles. So due to this equatorial bulge, the acceleration due to gravity at the equator is a little smaller compared to that at the poles. All these variations are very, very small. So sometimes you can neglect these variations in the value of g. And also there is a variation in the g due to the non-uniformity in the mass distribution. Okay. So on the surface of the earth and also inside the earth, the mass is not equally uniformly distributed. Okay. So there is a variations in the density. So, however, even though the variations in the G may occur due to the variations in the non-uniformity in the value density, these variations are very small. Okay, so sometimes in almost all cases we can neglect this variation.